Welcome back. I'm Muggsy, and today I'm going to explain how to do molar mass conversions. Before we practice some molar mass conversion problems, you should know about molar mass, what it is and how to calculate it, and also about the concept of the mole. What we're going to do today is we're going to kind of bring those things together to actually solve some mathematical problems. And basically, like any other time we're doing math and chemistry, we're essentially doing unit conversions. Almost all math you do in chemistry class is basically just unit conversions. So if you're not comfortable with unit conversions, check out my video on that. I've got a good one. Okay. So let's just do an example problem where let's say we had 35 grams of pure sodium metal, and we wanted to know how many individual sodium atoms that is. This is a problem we can do with what we already know about moles and about molar mass. The first thing we would want to do is we would want to convert grams of sodium to moles. And we can do that using the molar mass. And then finally, if we knew how many moles, it would be easy for us to get the number of atoms just using Avogadro's number. 6.022 times 10 to the 23rd atoms to every 1 mole. Just like there's 12 donuts to a dozen, there's 6.022 times 10 to the 23rd atoms to the mole. That's what a mole is. It's a counting unit just like a dozen, except massively bigger. It's this huge number instead of 12 because atoms are so incredibly tiny. Okay, so now that we have this problem outlined, let's actually solve it. And remember, it's all just unit conversions. So let's start by writing down our original value, 35 grams of sodium. And I wasn't joking, it really is all unit conversions. So let's make a conversion factor. Remember, whenever you're converting, you put the unit you're trying to get rid of on bottom, grams of sodium. I like to also include what element it is. And then you put the unit you're trying to get on top. Now, eventually we want to get atoms, but we can't do that right away. We have to go to moles first. So, moles of sodium. And in order to know how many grams 1 mole of sodium is, we just look at the molar mass of sodium. And for a pure substance, like pure sodium, instead of a compound like water or NaCl, the molar mass is exactly the same as the atomic mass. So all we have to do is look in the periodic table, and we see that the atomic mass of sodium is 23. So there are 23.0 grams to every 1 mole of sodium. Okay, if we do the math here, 35 divided by 23 is 1.52. We cancel the units that are found on both top and bottom, so grams of sodium cancels with grams of sodium, leaving the unit moles of sodium. And now we can do the second step of this problem, which is to go from moles to atoms. So I'm going to write 1.52 moles of sodium. And I'm going to multiply that by a conversion factor. I don't know what's going to go on this conversion factor yet, and I don't need to know because I'll just follow the rules of setting up conversion factors. So because I have moles of sodium here and I want to get rid of it, it has to go on the bottom there. So, okay, that makes it easy. Moles of sodium. And then what I'm trying to get is atoms of sodium, or sodium atoms is probably a better way of saying that. And so moles of sodium is going to cancel with moles of sodium, leave me atoms of sodium. Perfect. Okay. Now, how many atoms in a mole? Well, there's Avogadro's number, 6.022 times 10 to the 23rd atoms in every 1 mole. Remember, your conversion factor should always make sense when you speak it aloud. So for instance, if I put the 1 on top and Avogadro's on number, it would not make sense. I would say there's 1 atom to every 6.022 times 10 to the 23rd moles. No, that doesn't make sense. the opposite is true. There are 6.022 times 10 to the 23rd atoms for every 1 mole. Okay, perfect. So moles of sodium is going to cancel with moles of sodium, leaving atoms of sodium. And so this just becomes a pretty simple arithmetic problem, 1.52 times 6.022. I don't have a calculator in front of me, but I could basically do this math, right? 1 times 6 is 6, and then 0.5 times 6 is 3, so it's going to be something like 9 times 10 to the 23rd atoms of sodium. Let's go to the calculator to see what it would actually be. Okay, and if you put that in your calculator, you'll get 9.16 times 10 to the 23rd sodium atoms. Perfect. So again, as I said at the beginning, it's all just unit conversions. The only thing that we really needed to know here is how to calculate the molar mass of something. In this case, for pure sodium, it's just the atomic mass of sodium. And then what Avogadro's number is and how it corresponds to atoms and moles. Okay, let's do another problem. What if I had this huge number, 1.49 times 10 to the 23rd iodine molecules, not atoms, but molecules, because it's I2 instead of pure I. So we call that iodine the compound instead, iodine the molecule instead of iodine the element. Sometimes you could, I guess, refer to that as diiodide as well, but no one does that. And we want to know how many grams that is. Like what mass would that be if I had this many iodine molecules? Well, hopefully by now you know that we can't just go from the number of molecules to the grams, but we could, I suppose, go to moles and then from moles to grams. So that's how we're going to attack this problem. Because if we know the number of something, we can tell you how many moles of that thing there are, right? Moles is just a counting unit, like dozens or pairs or anything like that. It's just a huge number, 6.022 times 10 to the 23rd. And if we knew how many moles of something we have and we know what it is, we can go to the periodic table, calculate its molar mass, and then calculate its actual mass in grams. Okay, so let's do that. So let's start, as always, with conversion factors. 1.49 times 10 to the 23rd I2 molecules. We're going to multiply that by a blank conversion factor. What we're trying to get rid of is I2 molecules. Oh, it's a weird 2, but okay. I2 molecules. The thing we're trying to get is moles of I2. And then it doesn't matter what the thing is, if it's iodine, if it's sodium like the last problem, if it's tennis balls, whatever it is, we know that 1 mole is equal to 6.022 times 10 to the 23rd. Because a mole is a set counting unit, right? Okay, so all we have to do now is take our starting value, multiply it by 1, divide it by Avogadro's number, and then we get 0.247 moles. Molecules counts as with molecules, leaving moles of iodine. Okay, now that becomes the starting value of our second step, 0.247 moles of iodine. We're going to multiply that by a conversion factor. We're going to put what we want to get rid of on bottom. That's moles of I2. We're going to put what we want to go to on top, and we want to end up with grams. I guess we could say of iodine, although that doesn't really matter. And then if we wanted to know the mass of 1 mole of something, well, that's called the molar mass. And that definition makes sense perfectly, right? The mass of 1 mole, molar mass. Yeah, okay. To find the molar mass, all we need to do is add up the atomic masses of all the elements in that compound. And the only element in this compound is iodine. If we want to calculate this molar mass, let's look up the atomic mass of iodine in the periodic table. And we see that it's 126.9 grams per mole. Now, of course, this isn't iodine, this is I2, two iodines bonded together. So we're going to need to multiply that by 2 to get our final molar mass, which is 253.8 grams per mole. Okay, now that we've calculated our molar mass of iodine, we can put that in here. You could also round that up to 254, depending on what kind of math requirements you have. And so we're just going to take our number of moles, 0.247, multiply it by the molar mass, 253.8, divide it by 1, which means you don't have to do anything. Moles of iodine are going to cancel with moles of iodine, and we're going to be left with grams of iodine. So 0.247 times 253.8 gives us 62.7 grams of I2. And that's how you solve a problem like that. Again, it's all just conversion factors. So really make sure you know how to do your conversion factors. The only extra step here was we had to calculate the molar mass of I2, which is a little bit different from I1, but not that different. We just had to multiply it by 2 because there's 2 of them. And we get the molar mass 253.8. And we use that in our calculations to get our final mass of iodine, 62.7 grams. Okay, let's do a more complicated problem. Imagine I have 1 kilogram measured out to 3 sig figs of glucose, C6H12O6. You don't have to have that memorized. I usually ask my biology students to memorize it because it's such an important compound. But for chemistry, it's just another compound that we're going to use in an example problem. And let's say we wanted to know how many individual, let's not say atoms, well sure, let's say atoms. How many atoms of, let's say, oxygen are in that 1 kilogram of glucose? Well, this is going to be a much tougher problem because first thing we're going to need to do is we're going to need to convert from kilograms to grams. And then once we have the grams, we can convert to moles of glucose, C6H12O6. And then once we have the moles of glucose, we can get the moles of oxygen. And then once we have the moles of oxygen, we can get the atoms of oxygen. But let's just walk through that. That's kind of a really quick crash course. Let's go through and actually solve this problem piece by piece. Molar mass is in grams per mole. So anytime we're working with moles or molar mass, we can't really work with kilograms or milligrams or pounds or something like that. We need to work with grams. So let's start by taking our starting value, 1 kilogram, convert it to grams. You could just do this in your head, but let's just write it out, just practice these conversion factors. The unit that we want to get rid of goes on bottom. The unit that we want to go to goes on top. Then we put in the relationship that makes sense. I feel like I might make a mistake here, but maybe you can catch it. Oh, actually, no, I didn't make a mistake. I did it perfectly. There are 1,000 grams to every 1 kilogram. If I had flipped that, and said kilograms, grams. There are 1,000 kilograms to every 1 gram. Well, that doesn't make sense. Kilograms are big, grams are small. There'd be a lot of grams in a kilogram and not the other way around. So remember, you can always test your conversion factor by just thinking about it, speaking it aloud. 1,000 grams to every 1 kilogram. Okay, kilograms cancel with kilograms. 1 times 1,000 is 1,000. 1,000 divided by 1 is still 1,000. 1,000 grams. 1,000 grams of what? 1,000 grams of glucose. Now would be a good time to get in the habit of, along with your number, also include your unit and then also include what it is we're talking about. So in this case, the identity of the thing is glucose, C6H12O6. It takes a little bit of extra time, but it's a great way to organize your calculations, especially as you move on in chemistry class. These problems are going to get longer and longer and longer. Okay. So this now becomes the starting value of the second part of this problem. So if we have 1,000 grams of glucose, we want to know how many moles is that. Now, we want to get rid of grams of glucose. We want to go to moles of glucose. How many grams in every 1 mole? Well, in order to do that, we have to calculate, once again, the molar mass. So to get the molar mass of pure sodium, we just looked it up in the periodic table. It's 23. To get the molar mass of iodine, we had to look up the atomic mass of iodine, and then we had to multiply it by 2. In this case, we have a much bigger molecule, so it's going to be a more complicated process. So let's do that. We need to look up the molar mass of carbon. We need to look up the molar mass of hydrogen. We need to look up the molar mass of oxygen. We need to multiply them by the number of those that are in the molecule, and then we need to add them all together to get the overall molar mass of this big molecule that contains 6 carbons, 12 hydrogens, and 6 oxygens. Okay, so the atomic mass of carbon is 12.0 grams per mole. The atomic mass of hydrogen is 1.01 grams per mole. And the molar mass of oxygen is 16.0 grams per mole. I have these all memorized because these are really common elements, but you can look them up easily in the periodic table. Okay, then we need to multiply them by their the number of them that there are in our particular compound. So there's 6 carbons, there's 12 hydrogens, and there's 6 oxygens. And so 12 times 6 is 72 grams per mole. Twelve times 1 is 12, but it's also 0.01 times 12, so that's 12.12 grams per mole. And 16 times 6 is, I don't know, 60, 36, 96, right? I hope that's right. And then if we add all these up, 96 plus 12 is 108, plus 72 is 180.1, which we can just round to 180 grams per mole. It's a big number because it's a big molecule, because it contains lots of different things. 6 carbons, 12 hydrogens, 6 oxygens. The biggest one was the oxygens because they have a big mass to begin with. And so 16 times 6 is a relatively big number. Hydrogen's kind of an interesting surprise. There's 12 hydrogens, but it only accounts for a molar mass of 12 grams per mole because the mass of each individual hydrogen is so small, 1.01 grams per mole, because remember, hydrogen is the smallest element there is. Okay, so you add them all up, you get 180 grams per mole. That's our molar mass of glucose. So we can just plug that in here. And we have 1,000 divided by 180 is going to give us our final answer. Let me plug that into a calculator. 1,000 divided by 180 equals 5.56, we'll call that, moles of glucose. Grams of glucose cancels with grams of glucose, leaving the final unit moles of glucose. Okay, we're still not done. So now we know that if we had 1 kilogram of glucose, that equals 1,000 grams of glucose, which equals 5.56 moles of glucose. Now, if we know the number of moles of glucose, what's a little bit tricky here is we're not actually asking for the number of individual glucose molecules. We want to know the number of oxygen atoms. That makes this a trickier problem. So let's start with 5.56 moles of glucose, C6H12O6. We want to get rid of moles of glucose. And we want to get moles of just pure oxygen all by itself. And here we're thinking about a mole ratio for the first time. Mole ratio is just the ratio of one thing to another. So for instance, let's say I have a dozen bicycles. If I have a dozen bicycles, how many wheels do I have? Well, I would have 2 dozen wheels, right? Because the ratio of wheels to a bicycle is 2 to 1. There's 2 wheels on every 1 bicycle. And it's the same thing with moles. So if I have some crazy number of moles of glucose, how many moles of oxygen do I have? We just need to look at the number of oxygens in every glucose, just like we would look at the number of wheels on every bicycle. And here we can see that there are 6 oxygens for every 1 overall glucose molecule. See what I did there? We're looking for the actual number of oxygen atoms. And so whatever our number of moles are, we're gonna have to multiply that by 6 because there's 6 oxygen atoms in every 1 glucose. So if I have 5.56 moles of glucose, I have 5.56 times 6, something like 30 something moles of oxygen. Let's do that math now. So moles of glucose is gonna cancel with moles of glucose. 5.56 times 6, let me use my calculator. 33.4 moles of oxygen. Again, this number is 6 times bigger than that because we're looking at the number of moles of oxygen, not moles of glucose, because we're trying to get the number of oxygen atoms, not the number of overall glucose molecules, but the number of individual oxygen atoms, and there's 6 oxygen atoms to every 1 glucose. So to get our final answer, we just need to multiply 33.4 times Avogadro's number. I tend to just do it without the exponents and then throw them back on, so I just did 33.4 times 6.022 is 201 times 10 to the 23rd oxygen atoms, which means if we put that in scientific notation, we need to make our number 2 smaller, so we need to make our exponent 2 bigger. So 2.01 times 10 to the 25th oxygen atoms. Whew, that was a long ways to get there, but this was a particularly complicated problem. The thing I really want to impress upon you with these molar mass, mole calculation problems are calculate molar mass correctly as best you can, obviously. And then remember, outside of that, everything else is just unit conversions. Make sure that all your conversion factors make sense. They should when spoken aloud as a sentence. There are 180 grams of glucose to every 1 mole of glucose, that sort of thing. And then be sure that you're doing your unit conversions correctly, and you'll arrive at the right answer every time. So I hope this helps. Hope it wasn't too complicated. You should practice it a lot, and then you'll really feel a lot more comfortable with it. I'll see you next time.